Hi class, this is the first of several videos I'll be posting on electromagnetic waves, and this is the central topic in chapter 5 of our textbook. This is a very important topic in astronomy. In this chapter we're studying the nature of electromagnetic waves and the various types of electromagnetic waves, which includes the visible light that you see with your eyes. It also includes things like radio waves and microwaves and infrared light and ultraviolet light and X-rays and gamma rays. And these are all things that we study in astronomy because these are the various forms of electromagnetic waves that are emitted by various objects like planets and stars and galaxies and the universe as a whole. And the way that we study astronomy is we collect these various forms of electromagnetic waves and we analyze them. And this is how we extract information about these objects that we study in astronomy. So this is why this is such a really critically important topic to have some understanding of in order to really appreciate how astronomy is done. So it was in the mid to late 1800s when a scientist named James Clerk Maxwell realized that you can take the understanding of electric and magnetic force fields, which is something that was being very actively studied at the time. He realized that you could take those equations that describe them and combine them together and predict the existence of this electromagnetic wave, which is an oscillation of electric and magnetic force fields, and it propagates forward through space and it travels at the speed of light. And so it's just there's a lot of physics behind that, but that's kind of the quick little description right there. One of the things that distinguishes electromagnetic waves from other forms of waves that you might be familiar with, like water waves or sound waves or waves on a string, like if you play guitar and you pluck a string, a wave travels up and down the string. All of those types of waves require some medium, be it the air or the water or the string itself. They need something to travel through, whereas electromagnetic waves, since they're just composed of these invisible force fields, these can travel through empty space, and that's why we can collect the electromagnetic waves that have traveled through empty space from stars and galaxies, because they don't need anything to travel through. All right, so you can create electromagnetic waves of any wavelength, which is the size of the wave. It's the distance between successive peaks of the wave. You could imagine, like, here's an example would be like if you're sitting at the beach and you're watching the water waves come in, you're watching the waves come in. The wavelength of those waves is the distance between successive waves. You can measure that in feet or meters. Same thing with electromagnetic waves. They come in all different wavelengths. And all of these electromagnetic waves, they all travel at the same speed, which we call the speed of light. And it's so important we give it its own symbol, lowercase c, and it's measured to be 300 million meters per second. So in 1 second, a beam of light will travel almost exactly 300 million meters, which is approximately equal to the distance between the Earth and the Moon. So it's pretty fast. This is a really gigantic number. We've got a much better way to represent this number in science, and this is very helpful. It's more compact. It also makes doing calculations a lot cleaner and more meaningful in some ways. So we take this number, 300 million, and we're going to represent it in scientific notation as this, 3 times 10 to the 8th. These are the same number. And it helps to look at this intermediate step. We take 300 million, we can break it into 3 multiplied times 100 million, that's the same thing, and then 100 million we can represent in this compact notation, 10 to the 8th. 10 to the 8th means you take 8 tens and you multiply them together. If you take 8 tens and multiply them together, you get 100 million. Anyways, we take this number, 300 million, we represent it as 3 times 10 to the 8th. This is the same number, and the unit is meters per second. So that's the speed of light right there. Once again, you can create these waves of any wavelength. We use the Greek letter lambda to represent wavelength. And here is a chart of the various forms of electromagnetic waves. And again, what distinguishes them is their size, their wavelength. So the biggest waves we call radio waves, and these range from hundreds of kilometers down to approximately 10 centimeters. Once the waves are smaller than 10 centimeters, we stop calling them radio waves and we start calling them microwaves. But there's no difference between these. These are just smaller than these. That's the only thing. And there's no real well-defined cutoff. But approximately around 10 centimeters is where we change what we call them. Anything between about 10 centimeters down to about a millimeter, we call these microwaves. Things that are smaller than a millimeter, we start to call it infrared light or infrared radiation. And that's anything from a little bit less than a millimeter down to the wavelength of red light. And once we get into visible light, then we start using more unfamiliar units of measurement for distance. We'll use nanometers and micrometers. I'm going to describe those in the next slide. But anyways, smaller than infrared light, we call it visible. This is the stuff we see with our eyes. Smaller than violet, which is the shortest wavelength visible light, we call that ultraviolet. And then shorter than that is X-rays, and finally the shortest are gamma rays. So here are the various units of distance that we use to describe wavelengths of electromagnetic waves. Radio waves can be big, they can be kilometers in size. You probably know that a kilometer is 1,000 meters, and in scientific notation we can represent that as 10 to the 3 meters. Centimeter is 1/100th of a millimeter. Centimeter is 0.01 meters, so it's 1 divided by 100, and the way we represent 1 divided by 100 in scientific notation is 10 to the -2. So there's a centimeter. And you also notice that the 10 to the -2, one way to learn the significance of that is that you can take the decimal place and move it 2 spots to the right to get back to the number 1. That's why we use -2 right there as the exponent. Millimeter is 1,000th of a meter, so that's 0.001 meters in scientific notation. We'll call that 10 to the -3 meters. That's how we represent 1,000th, 1 over 1,000. Here are the unfamiliar units, most likely. The micrometer, we use the Greek letter mu for micro. The micrometer is equal to 1,000,000th of meter. 1 over 1,000,000 is 0.000001, and in scientific notation we call that 10 to the -6. A nanometer is 1,000,000th of a meter, and in scientific notation that's 10 to the -9, and this is actually going to be probably the most frequently used unit for wavelength that we'll be using in this class, because this is the most appropriate unit of distance when describing the wavelength of visible and infrared light. So we'll be using this a lot. Another way to distinguish these various forms of electromagnetic waves, rather than describing their wavelengths, is we can describe their oscillation frequency. And the way to think about this is, as these little wiggling waves are moving forward at the speed of light, they wiggle up and down, so they oscillate up and down. And so rather than describing how big they are, the wavelength, we can also describe them by the rate at which they wiggle up and down. So how many times per second does the wave wiggle up and down as it's traveling forward through space? And so that's describing its frequency. And very quickly, to describe frequency, we use a unit called the Hertz. So there it is spelled out. This is named after Heinrich Hertz, who was a German scientist. And here is the symbol, Hz, so Hertz. So 1 Hertz is 1 cycle per second. If it takes 1 second for it to wiggle up and down, that would be 1 Hertz. But in general, we'll be talking about much higher frequencies. So we'll be using kilohertz or kilohertz, which is 1,000 cycles per second. 1,000 Hertz, that's 10 to the 3 Hertz. Or we'll be using megahertz, which is 1,000,000 Hertz, that's 10 to the 6 Hertz. Gigahertz, giga means billion. So mega means million. So megahertz is 10 to the 6 hertz. Gigahertz is 10 to the 9 hertz. And then finally, terahertz would be a trillion hertz. So that's a trillion cycles per second.